Here is a question that I'd like us to ponder over as we go through the contents of this video. Learning or reverse engineering linear regression requires just one neuron and just an affine transformation. An affine transformation or a linear transformation is all that's required, and it's only one neuron that's needed to learn or reverse engineer linear regression. True or false? Let's now jump into a simple example. Let's use regression, linear regression, as the function that needs to be learned by our neural network. We've discussed already that neural networks can learn arbitrarily complex functions. They can really reverse engineer any piece of code at all. All that you need to do is to add enough layers to your neural network and wire them up correctly. Of course, this is sometimes easier said than done. But there is little ambiguity about learning linear regression. Linear regression is a straight line relationship of the form y is equal to wx plus b, and this pretty neatly fits in with the affine transformation that is performed by a single neuron. So we pass in a set of points into the neuron, and the output, once the neuron has been trained, is the regression line in the form of those constants w and b. Let's now double click on the neuron in this process. So the inputs are still all of the x values exactly as before, but now these are passed into an affine transformation unit inside a neuron of the sort we just looked at. Here, because the output of the affine transformation itself exactly mirrors the regression equation, we don't even need an activation function. As long as the values of w and b are indeed the best values, that is all that is required. That is the best fitting line for this set of points. This point is worth repeating because here the function that our neuron needs to learn is a linear one. We don't need an activation function. The affine transformation alone will suffice. Let's very quickly go over once again how this affine transformation works. It's just a weighted sum of the inputs with a bias added. The inputs are all of the x variables. These are the causal or explanatory variables which need to be linked or used to predict the output. The constants w represents the weights. These measure how much weightage each of the inputs should be given by the neuron. And the constant b is the bias. This will adjust the output of that weighted sum of w and x either up or down. We've already answered this question: where do the weights w and the bias b come from? And the answer is that they are determined during the training process. Remember also that in TensorFlow, these are variables. So the input values, the x values, are placeholders, but the weights and the bias are variables which will be determined for us during the training process. That training process is managed by TensorFlow, but we do need to specify an optimizer, a cost function, the corpus of training data, that's the input values, and the number of steps. We'll have more to say on the mechanics of the training process and on the optimization process in just a bit. We are going to actually implement linear and logistic regression, and for that, we need to understand what cost function we are going to go with. Let's just go with simple regression where we have one x variable. So we want to represent the values of the y variable in terms of a constant a and the slope b. Hopefully, in a perfect world, one set of constants a and b would be enough to perfectly fit all of the y values given the x values. But in reality, we have n equations and just two unknowns, so perfect equality will not be possible. We will have to live with a bunch of error terms or residuals. Let's call them E1 through En. This equation can now be represented in simple matrix form. We have a y matrix on the left hand side. This is equal to a constant a multiplied by a vector of ones plus a constant b multiplied by a vector of the x variables, and then we've got to add in a vector of all of the residuals. This is the matrix notation behind a simple linear regression. The best values of a and b are those which will minimize the sums of the squares of those residuals. This method is known as minimizing the least square error. Here, the error that corresponds to any one point xi, yi is obtained by dropping a perpendicular line from that point onto our regression line. The point of intersection will have the same x variable, after all the line is perpendicular, but it will have a different y value. And this difference between the actual and the fitted y values constitutes the error or the residual. These two terms are subtly different in a mathematical sense, but they can often just be used synonymously. The objective of linear regression is to minimize the sum of the squares of all of these errors. This implies finding the best values of the constants a and b. There is an infinite number of candidate lines. Let's, just for the sake of example, consider two. Let's call these line 1 and line 2. These have the parameters a1 and b1 and a2 and b2 respectively. Coming back to a single neuron, the training process needs to find some way, it needs to have some mathematical procedure for choosing the best such line. If there were only these two lines, it needs to know mathematically why it should pick line 1 rather than line 2. And the answer to this is via an optimization to minimize the least square error. So the optimizer will drop vertical lines from each point to each of the candidate lines. Then, for each candidate line, we will calculate the sum of the squares of the lengths of these dotted lines. Now, these dotted lines are, of course, the errors or the residuals. So, what the optimizer is seeking to do is to minimize these errors as measured by the sums of the squares of their lengths. And the line which has this property of all candidate lines, it has the lowest sum of the square of the errors. This is the best fit or the regression line. Now, there are many cookie cutter methods specifically designed for solving this regression problem. These include the method of moments, the method of least squares, and the maximum likelihood estimation method. But in reality, none of these is used quite directly by TensorFlow. When we implement linear regression in TensorFlow, we have a training process. That training process will go through an iterative set of steps, and those steps will determine the values of the weights W and the bias B. Also, just to be clear, this training process is global, as in it applies to the entire computation graph as a whole and not to an individual neuron. We will go through this process in more detail when we actually implement linear regression in TensorFlow in multiple different ways. Let's return to the question we posed at the start of the video. This statement is true. An affine transformation of any variable involves multiplying that variable by a constant and then adding a constant to it. So if you have a variable x, an affine transformation will be a function of the form wx plus b. This is exactly what one neuron accomplishes in its affine transformation portion. We do not need multiple neurons, nor do we need any non-linearity. So this statement on screen is true.